In order to understand how batteries work, because they work via a redox reaction, we need to talk about redox reactions. We need to go over those guys in painstaking detail here. Redox is short for reduction oxidation. It's an abbreviation. And these two terms, reduction describes the process of gaining electrons. So an atom that gains electrons, and oxidation describes the process of losing electrons. And we got a beautiful mnemonic device for you. Oh my goodness. And that mnemonic device is oil rig. Oil rig. Oxidation is loss, reduction is gain. Okay, that is our mnemonic device for remembering that oxidation is the process of losing electrons and reduction is the process of gaining electrons. There's another mnemonic device. It's Leo, the lion goes grr. That's just stupid. So Leo, losing electrons, oxidations, and then grr, gaining reduction. That's just stupid. Oil rig, folks. That's where it's at. Oxidation is loss, reduction is gain. So in a battery, which is what we're going to build up to, one of the sides of a battery is losing electrons, being oxidized, and it's giving electrons to the other side of a battery, which is being reduced, which is gaining the electrons. And if you force those electrons to travel through a wire to get from one end of the battery to another end of the battery, then you can pass that electron through those electrons through that wire to get from one end of the battery to the other, and that's a current. And then you can use that electricity to power a device. Okay. So, really what we have to do is we have to, before we can start building batteries, we have to understand redox reactions. We have to be able to identify, what is in a reaction is being oxidized, what in a reaction is being reduced, all that beautiful stuff. And in order to do that, we have to talk about some rules for assigning what are called oxidation states. And oxidation states are really like bookkeeping for electrons. And there are 4.5 rules. 4.5 rules. That's 4.5 rules. We'll talk about the half rules here in a second. What are the rules for assigning oxidation states? Well, the first two are so easy, it's not even funny because they don't deal with covalent compounds. It's the covalent compounds that make everything so tricky. Anyway, the first rule in assigning oxidation states is that a pure element, so the atoms of a pure element have an oxidation state of 0. So we need to go back to Chem 101 and we need to talk about the definition of an element. An element is anything that contains one type of atom. One type of atom. So for example, iron, that's one atom. So of course it's one type of atom. That's an element, right? But S6, that's an element. You say, wait a minute, there's 6 atoms there. Yeah, but they're all sulfur. That's an elemental form of sulfur. Bromine, one of the 7 Brinkelhoffers, right? So the 7 diatomics, bromine, iodine, nitrogen, fluorine, hydrogen, oxygen, fluorine, the 7 diatomic gas, or 5 of them are gases, 2 of them are not. One's a liquid, one's a solid. Anyway, the 7 diatomics, they're all elemental forms, right? C60, Buckminster fullerene, C60, that's an elemental form of carbon. The carbons would all have an oxidation state of 0. Okay. So, pure elements have an oxidation state of 0. Pure elements have an oxidation state of 0. And then the next rule is super easy. If you have an ionic compound, the charge of the ion is its oxidation state. So, for example, if I have sodium chloride, that's an ionic compound. Sodium has a +1 charge and chloride has a -1 charge. Those are the oxidation states. That sodium is in the +1 oxidation state, and that chlorine is in the -1 oxidation state. Charge is oxidation state. Okay, I mean, another example here would be like calcium bromide. Calcium is +2, and each bromide is -1. That's why you need 2 of them to cancel that out, right? So the charges of the ions are their oxidation states. Now, it's like that modus ponens thing, right? Okay, in philosophy. Listen, all charges are oxidation states, but not all oxidation states are charges. let me show you what I mean. Okay, the problem with this stuff and what makes it difficult is covalent or molecular compounds. They share electrons, so they don't have charges. So how do we keep track of the flow of electrons through covalent compounds when there's no charges to assign? Well, that's where we need these rules 3, 4, and 4.5 or 5 on there. That's where we need these rules for assigning the oxidation states of nonmetals in covalent compounds or molecular compounds. So here they are. It's pretty simple. If you have a covalent or molecular compound, oxygen has an oxidation state of -2. So the oxidation state of oxygen in a covalent compound is -2. Unless that oxygen is a weird oxygen called a peroxide, don't even worry about that. I'm not going to give you any peroxides, okay? But if you go on in chemistry, don't tell your don't tell your inorganic chemistry professor 2 years from now that your Chem 102 instructor never mentioned peroxides, because I did, and they're different. Peroxides have a -1 oxidation state for each oxygen, but they're special and reactive, and don't worry about it. So what does this mean? This means if I have a covalent compound like carbon dioxide, there are no charges in this. It's covalent. So what you do is if there's an oxygen, then you assume the oxygen is -2. Okay. And then what you could do is you could figure out the oxidation state of the carbon. Well, if each oxygen is -2 and there's two of them, that's a total of -4. This thing is neutral. Compounds are neutral. So the carbon must be in the +4 oxidation state. So each oxygen is -2, and then carbon must be +4. So by assuming that an oxygen in a covalent compound is -2, you can get the oxidation state of the thing that it is bound to, the other thing that it is bound to. For example, say you had NO. Well, again, oxygen in a covalent compound -2, which means that the nitrogen here must be +2. So the nitrogen in the +2 oxidation state. So by assuming the oxygens in a covalent compound have a -2 oxidation state, you can get the oxidation state for the other things. Okay. Alrighty. Now let's talk about hydrogen. You can assume that hydrogens in covalent compounds have a +1 oxidation state. So the hydrogen in a covalent compound is +1, So this comes in handy if I have, I don't know, say I have CO2H2. Say we have that. Well, now, covalent compound, all nonmetals. Each oxygen is -2, so that's a total of -4. Hydrogen, each hydrogen is +1. That's what rule 4 says. So two of those, that's +2. So what must the carbon be? Well, at the end of the day, this is a neutral thing, so it's got to add up to 0. So what -4 + 2? Well, the carbon must be +2. This carbon must be in the +2 oxidation state. So by assuming that oxygens are -2 and hydrogens are +1 in covalent compounds, you can usually figure out the oxidation state of everything else. Now, what if you have a covalent compound that doesn't have any oxygens or hydrogens? What do you do then? Well, that's why this is in red here, folks. You cannot always do this. You can only do this when, and you should write this down, there are no oxygens or hydrogens present. If there are no oxygens or hydrogens present, then it is safe to assume that halogens, those are the elements of group 17, fluorine, chlorine, bromine, iodine, astatine, you can then assume that halogens are -1, but only when there are no oxygens or hydrogens present. So let me show you. Talk about covalent compounds, right? So if you look at a periodic table, you know that staircase goes down the side of boron, right? You got the metals, you got the non-metals, with one exception. Hydrogen is actually a non-metal. An ionic compound contains a metal and a nonmetal, but a covalent or molecular compound contains only nonmetals. Okay, so that's what a covalent or molecular compound is. So let me give you an example of that 4.5 rule here. Okay, let's see here. Let's see. Let's do this. So if I have the covalent compound SF4 and it's covalent because sulfur and fluorine both above the staircase, right, as a covalent compound. If I want to assign the oxidation states of each element in this covalent compound, I have no hydrogens or oxygens present. If there's no hydrogen or oxygen present, then it is safe to assume that the halogen, group 17 element, is -1. And then I can use that to get the oxidation state of the sulfur. If each halogen is -1, and I got 4, that's -4, the sulfur must be in the +4 oxidation state, right, to make that equal to 0, because there was no charge written here. If there was a charge, then all the oxidation states had to add up to the charge. We'll talk about that in a moment. Okay. But listen, halogens don't have to be -1. If there's an oxygen or hydrogen present, then you assume -2 for oxygen and +1 for hydrogen before you do anything with the halogens. So let me give you some examples. Let's do the hypochlorite ion. That chlorine, which is a halogen, group 17, that chlorine is not -1. Right? You only assume halogens are -1 if there's no oxygen or hydrogen present. Okay, but if we look at this, we got an oxygen that's -2. So this is like saying what plus a -2 equals -1. Why is it going to equal -1? This is an anion, and the sum of the oxidation states have to equal the charge of the ions. Since this has a -1 charge, this chlorine must be in the +1 oxidation state. Think about it. 1 minus 2 equals -1. That's how we get that. I would like you to assign the oxidation state of the chlorine in chlorite, chlorate, and perchlorate. Go ahead, assign me the what is the oxidation state of the chlorine in this ion, and this ion? Go ahead. Okay. Oxygen, -2. So what -4 equals -1? The chlorine in this bad boy is +3. Oxygen, -2. So what -6 equals -1? The chlorine here is +5. And then look in here, oxygen, -2. So what -8 equals -1? It must be +7. Listen, folks, halogens can be all over the place. They can be +1, +3, +5, +7, or -1. It is only safe to assume that a halogen is -1 when there's no oxygen or hydrogen present in the covalent compound. Okay, so watch out for that. All right, I want you to practice some more. I would like you to do numbers 1 through 4. We actually already did 7, so you can cross off 7, and then we'll talk about 5 and 6. Okay, so I want you to try 1 through 4. Don't do 5 and 6 yet. Stay calm. Okay, I want you to try 1 through 4. I want you to assign the oxidation state of each atom in that compound. So I want you, for example, in number 1, I want you to tell me the oxidation state of sulfur and fluorine. Number 2, nitrogen and oxygen. You get the point. So I want the oxidation state of each compound in each one of those. Take a minute. Go ahead. All right, folks, here we go. Let's do this thing. It is safe at number 1 to assume that halogen is -1 because there's no oxygen or hydrogen present with it. So the sulfur is rocking a +6, right? Think about it. What -6 equals 0 plus 6. Here we got nitrate. The oxygen is -2. We got 3 of them. That's -6. So what -6 equals -1? Well, that nitrogen is in the +5 oxidation state. Taking a look at the ammonium polyatomic cation, hydrogen +1. So that's a total of +4. What +4 equals +1? That nitrogen is -3. Carbon, all by itself, pure element, 0. So there's our oxidation states, right?